Okay, that brings us to the twins paradox. So first we have to explain what the paradox is and then why it's a paradox, and then we'll see why it happens. So the twins paradox is another one of Einstein's thought experiments. The idea here is that we have a space traveler gets on a rocket and goes on a trip out to the stars. Meanwhile, their twin, who by definition is the same age, stays on Earth. Now, the paradox is when the rocket returns, the twins will no longer be the same age. And if it's a long trip, like a decades-long trip, one twin will be very old while the other twin is still young, like almost the same age that they were when they left. Now, first, that's weird, okay, and we'll explain why that happens in a moment. But first, the question is, well, why is this a paradox? Well, the reason why this is a paradox, the assumption here is that the twin is going to fly away for some period of time, and then the rocket will turn around and come back for some period of time. And we're saying that when the twin gets off the rocket ship, that they're not going to be the same age as their twin on the ground. And the example, we're going to do this for 1 hour. Okay, so flies away for 1 hour, comes back for 1 hour. When they get out of the ship, different amounts of time have passed for them. Now, why is this a paradox? Well, because we're saying the ship flies away from the Earth and then comes back. But if all motion is relative, wouldn't that be the same as the ship being stationary while the planet goes away and the planet comes back? Einstein said that the laws of physics are the same for everyone. So it seems like this should be a symmetrical situation. You can choose either one, either the ship or the planet, as stationary and treat the other one as the one that is moving. It seems like a symmetrical situation. Why would you get this difference where time passes differently for one twin than the other? That's the paradox. It seems like it shouldn't happen. It seems like it should be a symmetrical situation. Okay, so here's how it works. We need to go back to the same thing we just saw in the time dilation problem. In this case, we're going to have the ship as it flies away. It's going to fly away for 1 hour, and then it's going to come back for 1 hour. And the ship is going to make a flash every 6 minutes during the entire trip. So it's going to take off, fly away at this high speed that we were using in the previous example, making a flash every 6 minutes. Now, the planet is going to see the ship flash every 12 minutes as the ship flies away. And then when the ship turns around and comes back, the planet is going to see a flash every 3 minutes as it comes back, because it's the same situation we were looking at before. Okay, so let's do the math here and see how it turns out. The ship is going to fly away for 60 minutes, right? 60 minutes, and it's making a flash every 6 minutes. So that means it's going to make a total of 10 flashes. Okay, tell you what, I'm going to just do that on a separate one because it's going to mess me up. Okay, 10 flashes going out. Now, when the ship turns around and comes back, it also flies back for 60 minutes. Come on, we can do this. There we are. The ship flies back for 60 minutes, so it makes 10 flashes coming back, okay? Total of 20 flashes. And the ship has experienced 120 minutes, which is 2 hours, okay? 10 flashes times 6 minutes is 60 minutes. 10 flashes times 6 minutes coming back, 60 minutes, total of 120 minutes. Super. All right. Now, what does the twin who's on the Earth see? All right. As the ship goes away, the twin on the planet is going to see 10 flashes, because one thing they have to agree on is the number of flashes. They live in the same universe. So if one twin produced 20 flashes, the other twin has to see 20 flashes. That's something they have to be able to agree on. So as the ship is flying away, the twin on the planet sees 10 flashes every 12 minutes, which is a total of 120 minutes. And then when the ship turns around and comes back, the twin on the ground sees 10 more flashes, sees one every 3 minutes, which is a total of 30 minutes. So the total time is 2.5 hours, 150 minutes. Okay? So to summarize, the twin makes 20 flashes one every 6 minutes, 10 flashes on the trip out, 10 flashes on the return trip, total of 120 minutes, 2 hours for the whole trip, just like we said, a 2 hour trip, 1 hour out, 1 hour back. The twin on the ground sees all 20 flashes, 10 that were made as the ship went away, and 10 that were made as the ship came back. And it comes out to be a total of 2.5 hours. Now, it looks like some sort of sleight of hand trick or something. And this is a slightly simplified version of this, but this is the effect, and the effect here is valid. The math is slightly more complicated than this, but the effect is the same. This is not some math trick. This actually happens in the actual universe, okay? Now, what if, just for the sake of convincing here, so what this means is, by the way, that the twin who stays home, stays on the Earth, will age more than the twin that goes in the rocket ship. And if this was a decades-long trip and it went much, much faster than this, closer to the speed of light, then you'd have the situation where the twin on the ship would think that they'd only been gone for a day or a week or maybe a year. But the twin on Earth would think that it was a lifetime, and it would be like 60 years had gone by. Okay, now let's look at from the other point of view, just in case you think it may make a difference here. So this time we are going to have the planet make the flashes, okay? So before we had the ship making the flashes, and maybe that'll affect the outcome here, because we said this was a symmetrical. Well, the paradox was that this appears to be a symmetrical thing. So first we had the ship making the flashes. Now let's have the planet making the flashes and see how it works out. Okay, so again, the ship flies away for 1 hour, then it comes back for 1 hour. And we are going to, yeah, okay, this is how we'll do it. So the ship sees a flash every 12 minutes, okay? So the ship flies away for an hour, that's 60 minutes, and sees a flash every 12 minutes. So that means it's going to see a total of 5 flashes, okay? It's going to see a total of 5 flashes as it flies away. 5 hours times 12 minutes for 5 flashes times 12 minutes per flash is 60 minutes. Once it's 60 minutes has gone by, then it turns around and comes back. And this time it sees a flash every 3 minutes, which means that it's going to see a total of 10 flashes. 10 flashes. We'll put that in here. I'm sorry, 20 flashes. I can math. Okay. 20 flashes coming back. All right. 20 times 3 is 60 minutes. So the twin on the ship sees 5 flashes on the trip out, 20 flashes coming back because of time dilation. That means that the ship sees 25 flashes. Now again, laws of physics are the same for everybody. So that means that if the ship saw 25 flashes, that means that the twin on the ground had to make 25 flashes. But he or she made those flashes every 6 minutes. And 25 times 6 is 150 minutes, and it's 2.5 hours again. So it doesn't matter if the ship is making the flashes or the planet is making the flashes. The effect is the same. The twin that stays home, that stays on the Earth, ages more than the twin that's on the planet, than the twin that's on the ship. The twin that's on the ship will be younger. This is weird. Now, why is it? And why does this happen? Well, the answer is, if you want to pause it here to think about it and scratch your head and see if you can figure out what the deal is here. Let's see. We'll find it here. The problem is this one. That's your hint. Okay. The first postulate, Einstein's first postulate, is that the laws of physics are the same for everyone as long as they are not accelerating. That is the key, as long as they are not accelerating. Okay, now why is this important? The universe behaves differently if you are in an accelerated frame of reference, if you're on something that's accelerating. So to think of the trains here again. If the train is stationary and you drop a baseball, it will fall straight down into your hand. Okay, and likewise, if the train is moving at constant velocity down the train track at 100 miles per hour, but it's not accelerating, it's constant velocity. If you drop that baseball and you're on the train, it will drop straight down to your hand. The laws of physics are the same for you whether you are moving or not. However, what if you're accelerating on that train? What if the train is speeding up markedly? As soon as you drop the ball, if you're accelerating, the ball is going to appear to go sideways because you leave it behind. It's going to appear to go toward the back of the train because the train is speeding up out from under the ball as the ball falls. Something is pushing the train forward, but not pushing the ball forward. So the train starts to run ahead of the ball. If you're holding an open soda in your car and somebody slams on the brakes or steps on the gas, the soda will slosh out because there are different forces acting on different things. You are accelerating, so things behave differently. Things appear to behave differently. So in our twins paradox here, the twin who is on the spaceship, we've been saying, goes out for 1 hour and then turns around and comes back for 1 hour. But when you think about it, even in that simple phrase there, he goes out for 1 hour and then turns around and comes back at 1 hour. His speed has changed, his velocity has changed incredibly, hugely. Is that word? He's gone from half the speed of light to the upper right to half the speed of light to the lower left. That is a gigantic acceleration. You'd notice. You'd have to have some special G suit or something to keep from being squashed like a bug during that acceleration. And even if it was a gradual acceleration, so it was survivable, slowing down to a stop and then turning around and accelerating at a reasonable rate so it can survive the acceleration, there still is a long period of time where the twin on the ship is experiencing an acceleration. But the twin on the ground on Earth is not experiencing that acceleration. So that means that the laws of physics actually change for them and they experience the universe differently. Okay, so the answer to the twins paradox is that the twin on the spaceship has accelerated, and that changes it's no longer a symmetrical situation, and they will experience time differently. Now, how does this work when we talk about the original one we talked about where the spaceship was going from the blue planet to the green planet? Okay, if we had a twin on each planet here, their clocks would not agree about how much time, or I should say it this way, if we had the twin on the spaceship and it just stopped on the green planet, the spaceship's clocks would not agree with the clocks back on the blue planet where they left. But they can't put their clocks side by side to compare. Okay, because what's happened is the spaceship has accelerated, gone really fast, and then it slowed down and stopped and landed on the green planet. So they've experienced an acceleration that the people on the blue planet have not. Okay, and now they're on different planets, and they can't set their clocks physically next to each other to see if they're marking the same time. The only way they could do that is if the twin on the blue planet got in a spaceship, flew to the green planet, and then got out, and then they compared their clocks. And when they do that, now their clocks will agree again because the planet who was on the blue planet, made the second trip, now they have experienced the same acceleration, so now their clocks agree again. But in the twins paradox situation, where one ship goes out and comes back, now only one twin has experienced the acceleration, so the clocks don't ever agree again. Okay, that's enough for one day. Weird stuff. What you need to be able to do is at least describe the twins paradox, explain why it is a paradox, and be able to explain the explanation for it about the one twin accelerating. Okay, that's enough for one day, and we will see you next time.